When I ask my students to draw the Lewis structure of ozone, some students draw the molecule like this, and others like this. The lone pairs of electrons and formal charges are included. Notice on the left, the molecule is drawn with a double bond between oxygens 1 and 2, while the third oxygen is bonded to oxygen 2 with a single bond. The opposite is true in the molecule on the right. Then the obvious question arises. Which is the correct way to draw the Lewis structure for ozone? The answer may not be what you expect. Both are called valid Lewis structures for ozone. Notice how the octet rule is satisfied for all oxygens. These are called resonance structures. Here is the first definition for resonance. Multiple ways to draw a Lewis structure for a molecule without breaking the octet rule for second row elements. This definition usually will suffice for general chemistry students. We can say that these are resonance structures for ozone. For organic chemistry students, we can say resonance structures are different Lewis structures where the atom placement is the same, but the electrons are drawn in different locations, again, without breaking the octet rule for second row elements. These two definitions are saying the same thing, with the second specifically naming the different locations of the electrons. This is an important concept moving forward. Between resonance structures, we draw a double-headed arrow. This symbol is used in chemistry to refer only to resonance, and not to be confused with the forward-backward arrows used to represent chemical equilibrium. It's also important to note that this is not a chemical reaction. The double-headed arrow represents resonance, but the molecule is not moving back and forth between structures. In other words, the electrons aren't in one position exclusively, then move to another location. Again, this is an equilibrium. Here's another question. Which resonance structure is more stable? To determine stability of resonance structures, we must analyze any formal charges. In this case, we see both structures have an oxygen carrying a formal charge of -1, and both have a formal charge of +1 on the central oxygen. In the case of ozone, these resonance structures are equal. Let's go back to the original question, which is the correct way to draw the Lewis structure for ozone. These are two valid Lewis structures for ozone. Lewis structures just show us the possible electron arrangements, but physically, ozone actually exists as an average of the two molecules. This is called the resonance hybrid. Let's focus on the hybrid for now. We show partial double bonds or pi bonds between oxygens 1 and 2 and between oxygens 2 and 3. You see the broken lines representing the partial bonds. The electron density is actually spread out between the three oxygen atoms. We can also say that these pi electrons are delocalized. Now we can add to our definitions by saying that in resonance, the electron or charge density is spread out over a larger area or delocalized, thus stabilizing the molecule. We can say that ozone is resonance stabilized. Acetate is a classic example where two resonance structures can be drawn. Here's the second. Notice, each structure shows the octet rule satisfied for all carbons and oxygens, but you can see from the locations of the double bond, lone pairs, and formal charges, the electrons are in different positions. And the resonance hybrid looks like this. What about resonance structures that are not equal? Consider the resonance structures of dinitrogen monoxide, NO2. They all contain a central nitrogen atom with a formal charge of +1. But in the first structure, the other nitrogen carries a formal charge of -1, while the middle structure has the oxygen carrying the -1 formal charge. The last structure shows a nitrogen with a -2 formal charge and a +1 formal charge on the oxygen. Clearly, they are different. So how do they contribute to the resonance hybrid? For that, we must review the stability of resonance structures. The most stable structures will contribute the most to the resonance hybrid. In evaluating the stability of resonance structures, there are three main rules. First, structures are most stable when there are full octets and as many bonds as possible. Second, structures are most stable when the formal charges are as close to zero as possible. And third, if there are negative formal charges, they should be located on more electronegative atoms. Now let's return to our dinitrogen monoxide example. The last structure would be considered the least stable because there's a -2 formal charge on a single nitrogen atom. That would be too much of a charge on nitrogen considering that there is a more electronegative atom, oxygen, nearby. So we can ignore this third structure. In comparing the first two structures, we can see there's a formal charge of -1 on the nitrogen atom in the first structure, and a formal charge of -1 on the oxygen atom in the second structure. Based on the rules, the more electronegative oxygen atom will carry the formal charge better, stabilizing the structure. We can say the second structure is a major contributor to the resonance hybrid. The first structure would be a minor contributor to the resonance hybrid. Carbon dioxide is very similar. Notice in carbon dioxide, three resonance structures can be drawn. The middle structure shows formal charges of 0 for all atoms, thus would be the most stable structure and the major contributor to the resonance hybrid. The others would be very minor contributors to the resonance hybrid. Next, let's show the delocalization of electrons using electron pushing arrows. Drawing resonance structures will be a lot easier if you can identify a few types of bonding patterns. Here are the most common: the allylic lone pair, the allylic positive charge, a lone pair adjacent to a positive charge, and conjugated pi bonds in a ring. First, let's review some rules. Arrows start on a pair of electrons and point to where they are ending in the new resonance structures. An arrow can start on a lone pair, like this, or a pi bond, like this. The new structure looks like this. Notice the first arrow shows the lone pair going between atoms to form a new pi bond, and the second arrow shows the pi electrons moving to the top oxygen to give the oxygen a third pair of electrons and a formal charge. Next, a full-headed arrow represents a pair of electrons moving. Finally, never break sigma bonds. Sigma bonds only break in chemical reactions. Resonance structures are not products of a reaction. Sigma bonds are localized. while the pi electrons or lone pairs of electrons can be delocalized, which is what we are showing in resonance structures. You can only move lone pairs or pi electrons. Now, let's do some examples. The allylic positions are those atoms that are bonded to sp2 atoms. Here we have a carbon-carbon double bond, so these are sp2 carbon atoms, and the atoms that are bonded to these two atoms are in the allylic positions. There are the three hydrogens, and then here's a carbon with a lone pair of electrons. This is called a carbanion. It's the formal charge of -1 on a carbon. So we can draw a resonance structure. So here are arrows. I'll draw them in red. The arrow always starts on a pair of electrons and goes either in between carbon atoms, which I'll show here. So this represents a new bond. I'm using the full-headed arrow to show a pair of electrons is moving. We can't break the octet rule for this carbon, so I'll show these pi electrons going on to the next carbon atom. Here's the double-headed arrow to represent resonance, and my new structure looks like this. Because there's a negative charge on a carbon atom in each case, these are equal resonance structures. Here's another example of an allylic lone pair. Another helpful tool is to find functional groups. In this case, here's an amide functional group. I recognize the oxygen-carbon double bond, the carbonyl group. The atoms that are bonded to these atoms, the sp2 atoms, are in the allylic positions. In this case, the oxygen isn't bonded to anything. Now be careful, these lone pairs on oxygen are not in the allylic position. But carbon is bonded to this methyl group, which does not have a lone pair of electrons. But it's also bonded to the nitrogen, which does have a lone pair of electrons. So here we can draw a resonance structure. From the lone pair of electrons in the allylic position, I'll draw an arrow going in between those two atoms. And I can't break the octet rule for carbon, so I'll move the pi electrons over to that oxygen atom. Here's my double-headed arrow to represent resonance. There's a double bond between carbon and nitrogen, and now a single bond between the carbon and the oxygen. The oxygen now has 3 lone pairs of electrons. Let's not forget the formal charges. A negative on the oxygen. Here's a nitrogen with 4 bonds, so we'll draw a positive there. And these are resonance structures. As you can imagine, the resonance structure that has fewer formal charges, in this case the first structure has 0 formal charge all the way around, would be the most stable. So while there are resonance structures that can be drawn, they're not equal. The first one would be the major contributor to the resonance hybrid. Here's an example of an allylic positive charge. Again, a carbon-carbon double bond is right here. These are sp2 carbons. The atoms that are bonded to these two carbons are in the allylic position. you'll notice that in one allylic position, you have a carbon with a positive charge. This is called a carbocation. What's special about the carbocation, or this carbon with a positive charge, there's only 3 bonds on it. That means it has an empty p orbital that is available for accepting electrons. So in this case, we can draw a resonance structure where pi electrons from this double bond can go right next door and form a new bond here. So here's my resonance structure. I'll draw the double-headed arrow to represent resonance. The 4-carbon chain. Now there's a double bond right in that center between those middle 2 carbons. And now that last carbon loses that pi bond, loses that pair of electrons, and becomes positive. Here's another example of an allylic positive charge. In this line angle structure, you'll notice 2 sets of carbon-carbon double bonds. In the first set, you'll notice there's no lone pairs or positive charge in the allylic positions, but relative to this double bond, you'll see there's a positive charge in the allylic position. That means that carbon only has 3 bonds and an empty p orbital. So it can accept a pair of electrons from its neighbor. So these pi electrons we can draw just like this. The full head shows a pair of electrons moving. Here's my double-headed arrow to represent resonance. That first double bond is still there, but now I'll draw a double bond on the other end. And now this middle carbon carries that positive charge. Now, something special happens here. Notice I introduced this example by showing this double bond, and its allylic positions doesn't have any positive charge. Well, now it does in our second resonance structure. So now these electrons can move over here, and we can actually draw a third resonance structure. So here's the double bond at the end, which I showed right here. And now we can draw a double bond right here. And now this carbon, losing that pair of electrons, becomes positive. This is an interesting example because you can see that this structure is resonance stabilized. The electrons are delocalized. They are allowed to spread out through the entire molecule. That positive charge is allowed to spread out between several different carbon atoms. Here we see a lone pair of electrons adjacent to a carbocation, or a carbon with a positive charge. This happens from time to time in organic chemistry. This carbon right here sometimes will lose an atom, perhaps a hydrogen, in an acid-base reaction or some other type of leaving group. And this carbon loses that bond, then becomes a carbocation. So you can imagine now this carbon is sp2 hybridized, and it's missing that pair of electrons. So we can draw a resonance structure where the lone pair comes in between the 2 atoms and forms that extra bond. You can see in the new structure, the oxygen now carries the positive charge. There's a double bond between the carbon and the oxygen. And the second structure would be the more stable structure, since the octet rule is satisfied for both carbon atoms and the oxygen atom. And for this example, we'll show something here that is pretty common. You'll see lots of these in organic chemistry. This is a special molecule. You have this 6-carbon ring, and you see alternating double and single bonds. So you see a double bond and then a single bond between carbons, a double bond and a single bond. This is called a conjugated system. That means alternating, double, single, so forth. And so these are double bonds, so these are pi electrons, and we call them conjugated pi bonds in a system. There's a functional group here that we'll come across. This is called an arene or aromatic functional group. All of these carbons are sp2 hybridized. They all have the unhybridized p orbital. If you think of shapes, these are all trigonal planar, so this ring is actually flat, and then those unhybridized p orbitals are just perpendicular to the ring. And so you can think of those pi electrons as just sitting on top of the ring. And this is a pretty simple system to draw a resonance structure for. You can just move those electrons around the ring. And I think the point here is that this is a different way to look at the molecule. And in the resonance hybrid, what you should think about when you see this example of the arene or aromatic functional group or the aromatic ring is you want to think that those pi electrons are just kind of sitting on top of the plane, and they just fill that space. They're allowed to spread out. And so that's why you see a lot of these in organic chemistry and biochemistry. They're pretty stable, and you got those pi electrons just spread out and around the ring. So you can draw the resonance hybrid like this. Sometimes you'll see it in textbooks as just a circle, and so that just means that the pi electrons are around the ring. So on average, the molecule exists as a hybrid. It exists as partial double bonds all the way around.